Well, we are jumping into chapter 10 today. We're skipping over 10.2 and going straight into, skipping over 10.1, going straight into 10.2. Now, 10.2 is more hypothesis testing. Notice the name is Inferences for Two Population Means, sigmas assumed equal. So a couple things going on here. One, it's called inferences, meaning we're doing hypothesis testing again, but we're doing confidence as well. Also notice it's two population means. So instead of comparing one population to a number that we knew from before, we're comparing two populations to each other to see if they have equal means or if there's a difference. And then lastly, notice it says sigmas are assumed equal. So what we're assuming is that both of the populations that we have the same standard deviation. And for that assumption, if they're close to being the same, we don't have to know that they're exactly equal. This test is what we call robust enough that if there's slight variations in the population standard deviation, going to be okay. But let's talk quickly about that. If the sigmas are equal or approximately equal, then we pool the data together. For our calculations. And again, the computer's going to do all the calculations for us. So for us, we're just going to use the TI-83 or the TI-84, whichever we have. But it's going to ask us, do we pool the data? And we're going to have to know, well, if the sigmas are equal, it can be assumed close enough to equal, then we pool the data. What that does by pooling the data, it helps us reduce our probability of a type 1 error. Remember, that's rejecting something that was actually true. So we want to pool the data when we can. And so we can if the standard deviations are assumed equal. And we'll put it right here so that we have it in front of us. If sigmas are not assumed equal, do not pool. And calculator says unpooled. Actually, it just says pooled, yes or no. Do not pool the data. That's actually going to be the only difference between these two sections that we do, is whether we pool or do not pool the data. So let's go ahead and get started. We'll do a couple examples from each section that we know what's going on. And I'm going to jump right into a problem. And I've got something that I'm going to do today that I think might help us out. I'm going to, when we do a problem, instead of just referring you to the page, let's go ahead and do this. I'm going to grab a picture from my file, and I'm actually just going to put it right there so we have the problem. All right, so now when we go to look at this, we can actually go through and see what's happening. So problem 1045, this is from our textbook. I just pulled it straight out. It says doing time. The Federal Bureau of Prisons publishes data in prison statistics on the time served by prisoners released from federal institutions for the first time. Independent random samples of released prisoners in the fraud and firearms categories yielded the following information on time served in months. So they give us the different times. They give us the data. It says at the 5% significance level, do the data provide sufficient evidence to conclude that the mean time served for fraud is less than that for firearms offenses? Notice fraud's the first one they give us. So I'm going to say population is equal to fraud. And we'll also say population 2 is equal to firearms. And so we'll use subscripts. Notice they did that at the bottom. It says note X bar sub 1 is 10.12 years. I guess these are in months. And S sub 1, 4 months. X bar sub 2 and S sub 2, they give us those data values as well. So what we're going to do on this data in a list 1 and list 2, because now that I have two populations, they'll go in separate lists. I could do that, but since they've already given me these calculations, for our first example, we'll just go with what they've given us for those calculations. Okay, so let's go ahead and get started. For a hypothesis test, we always start the same way. We state the null and alternative hypothesis. The null hypothesis, notice again, we always use an equal, mu sub 1, so the mean of population 1 is equal to the mean of population 2. And then our alternative hypothesis, that's answering the question, what they say. Do the data provide sufficient evidence to conclude the mean time served for fraud is less than for firearms? Well, since mu1 was for fraud, we're going to say, oh, is that average less than the average for population 2, the firearms? In my mind, I'm saying I sure hope it is, because fraud is things like computer fraud, maybe somebody using your credit card, which is a bad thing. But when you compare it to firearms, I'd rather somebody steal my credit card than pull a gun on me. Just being honest with you. So hopefully this is going to be, we're going to reject the null hypothesis, but we'll see what's actually happening out there. Okay, so I've got my hypotheses. So now notice I have standard deviation of the samples. So these have to be t-tests. Okay, I don't have sigma. I'm assuming they're equal, but I don't have them. Now, it says in the reading before these problems, it says preliminary data analyses indicate that you can reasonably consider the assumptions for using pooled T procedures satisfied in the exercises 1045 to 1050. And it says for each exercise, perform the required hypothesis test by using either the critical value approach or the p-value approach. We always do the p-value approach. We're going to continue to do that same thing. Okay, so this time what we're going to do on the calculator, we still go into stat and tests, but what we're going to do, it's called a two-sample t-test. So it looks like this on the calculator, and we'll see it in just a minute. It's a two-sample t-test. And that stands for two-sample t-test because we have a sample from two different populations, or obviously we have two samples. Okay, so let's go through that, and we're going to do that. So let me flip over to the calculator. Now we need all this data. The good part is, since I took this straight from the book, I don't have to take a picture of this or write down these numbers or anything else. I'm able to just flip over and look in my book, so I still have all the numbers. So you may have wanted to write those down or something. But, oh look, I've got a nice, hopefully when you look at that, you're thinking, hey, that looks kind of right skewed to me. It's definitely not normally distributed. All right, so anyway, depending on what we see. But let's go ahead and do this. We're going to go stat, tests. Now this time, notice it's a two-sample t-test. It's down at number 4. You can either arrow down to 4. I just hit the number 4. Here, this time I'll arrow down so you see exactly which one I'm talking about. So that's where I'm going, two-sample t-test. I hit enter. Again, if I just hit 4, I didn't have to go enter. It says, do we have the data? Notice it lists list 1 and list 2. No, I don't have the data. I have the statistics. Actually, I do have the data, but they gave me the statistics, and that's what I'd rather enter. So they say, okay, start listing things. What is X bar sub 1? So from the previous page, what we saw, they had listed this for us. The X bar sub 1, meaning for the first sample, is 10.12 with a standard deviation of 4.9. The sample size, they don't tell us. I have to look at the data. There's 1, 2, 3, 4, 5. There's 10 data values. X bar sub 2, 18.78. And S sub 2, 4.64. N sub 2, there's also 10 there in that second sample. And then they say, okay, what's your mu sub 1? Is it not equal to mu sub 2? Nope, for the alternate, remember it's less than. So make sure you Choose the correct one. Now here's where it says pooled, no or yes. Well, this time they said we can assume that the population standard deviations are equal. So we're going to say yes. We're going to go ahead and pool the data here. And then let's arrow down, see what they have. Now we're just ready to calculate. So let's go ahead and calculate. Now, this stuff I'll need to write down because I don't know what they are. I won't remember them when I go to the next page. So let me jot these down real quickly. And I've got, let's see, my t value is negative 4.0581. I don't know on when you're doing the homework online, how many decimals they're going to go to. That's often just 2 decimals. But, and then the p-value is 3.6, we'll call it 3.69. We'll round that 8 up. But notice it says e to the negative 4, and we'll address that in just a second. So let's flip back to our page so we can see what we're doing. Okay, so they gave us the value for t, which was negative 4. I'm just going to go to 2 decimal places. It was 0.58, so the p value. Now here's where we need to be careful. You've probably seen this before, but I don't think we've done one in the lecture like this before. 3.69, and then it had some other stuff, but at the end it said e negative 4. And I know there's something weird going on because that p-value of 3.69, remember p stands for probability. And also remember, probability can never be above 1. I can't have a probability of 3.69. That'd be 369%. That's impossible. We can't go above 100%. Everybody knows that. Okay, so what this is doing, remember this e to the negative 4 over here? That's really saying times 10 to the negative 4 power. So we need to take this 3.69 and we need to move the decimal 1, 2, 3, 4 places over here. And so that's the new place that it's going to be. Let me do this in blue so we see that I added all these zeros. So now if I write the p-value, the way I'm actually going to write the p-value is to 4 decimal places. That 3 would round up to a 4. So it's going to be 0.0004. And remember, we're checking to see if that's less than or equal to what they gave us as the significance level. Off here to the left, they gave to it at 5%, so that's 0.05. Again, if you need to go to percentages to make sure that you're doing it correctly, make sure you do that. So this, if I move the decimal 2 places, we're at 0.04%, still really tiny. And this one would be 5%. And we say, well, clearly 0.04% is less than 4%. And since it's less, we're going to say, oh, if that's the case, I'm going to reject the null hypothesis. And since I reject the null hypothesis, I say, oh, I don't think the difference was just due to sampling error. I don't think these 2 population means really are equal. I think it's the alternative that mu sub 1 was actually less than mu 2. And so now we can answer the question and say, yes, it appears, I didn't spell appears right. It appears, I need to learn how to spell. It appears the mean time for fraud is less than the mean time for firearms. Offenses. In the world, do you spell offenses? Offenses. It's not a very good E, but we'll make it do. Okay, so anyway, there's my conclusion. So that was pretty straightforward. Now, here's what I'm going to do. They didn't ask us on this problem, but we're going to use the same problem, the same data, and we're going to go ahead and we're going to flip that. And what we're going to do with it is we're going to do a confidence interval. So let's do the same thing, and let's state this. I'm going to say, we'll call it part B. find a 90% confidence interval for the difference in prison times. I don't know how to spell prison either. And we could be more formal with that and talk about what they are, but we already know what they are, so we won't take our time to do that. But here's the idea. So just as before, instead of doing a 2-sample t-test, we just do a 2-sample t-interval. Now, as usual, after I find the interval, I need to interpret it because it doesn't help me to find an interval if I have no idea what it means. So let's jump back into the calculator. And here's what's nice. It keeps all the statistics that we put in there. It keeps all that. So we have almost nothing to do. So I flip back to the calculator and I go stat tests, but now it's a 2-sample t interval. Notice down at number 9, we have 2-sample z interval. So I'm going to go, now I do have to arrow down to it. If I don't arrow down, if I just try to put in 10, wow, I arrowed a little bit too far. Then it'll just, as soon as I hit the 1, it'll register a 1. So, I guess it was a 0. I could have just hit a 0. All right, so anyway, enter it. Notice at the top it says 2-sample t interval. It says stats, but notice those are the same numbers already plugged in. So we've got the 10.12, the 4.9, sample sizes were both 10, 18.78, and 4.64. That's everything we put in before. We just need to go down and change our confidence level. All right, so our confidence level, let's put that in. We said a 90% confidence interval. Pooled, yeah, we're still keeping that as yes. And then we calculate, and bang, it gives us the interval right away. All right, so this one I'll need to write down. 12.3, negative 12.36 and negative 4.96. Let me tell you something that you may have picked up on already. The reason that those are both negatives is because 0's not in the interval. And what does that mean? Well, let's flip back up here real quickly. If we're assuming in the null hypothesis that mu1 is equal to mu2, that means the difference in the means is 0. If they're equal to each other and we subtract them, we get 0. If 0's in my interval, now actually this only works for a 2-tailed test, and this was a 1-tailed test, but it will still show in this direction. If 0 is in there, it would imply that these might be equal. The population means might be equal. Since there's no 0 in there, they're both negative. It means they can't be equal. So my 2-sample z interval is negative 12.36 to negative 4.96. And so that negative, if I did that, it meant mu1 minus mu2 equals a negative number. That means mu2 had to be bigger. So I always this, whatever this sign is here, and I speak of it in terms of the first population. Remember, our first population was fraud. So what this implies, fraud was less time. If that was a plus, it would mean fraud was more time, or whatever population 1 was. If it's negative, population 1 was less than the other. If it's positive, population 1 was more than the other. So when I word this, we can be 90% confident that the average time for fraud is between 12.36 and 4.96 months less than the average time for firearms. And there is our interpretation. And the interpretation is important because if you just are doing some study or a paper or something and you turn this into your boss or your teacher or you publish this and you just give them those numbers, most people are going to look at that and say, okay, I see these numbers, but what does it mean? You need to lay it out. Oh, it's between 12.36 months less and 4.96 months less if you're convicted and put in prison for firearms, for fraud, than if for firearms. And you could flip that around and say, oh, if you're convicted for firearms, it's somewhere between 4.96 and 12.36 months more on average for firearms than it was for fraud. Okay, so we do definitely see that supports the fact that we rejected the null hypothesis, because in no way does it look like firearms could be less than fraud. It was always fraud was less or fraud was less. I don't know how much less, but somewhere between 12.36 and 4.96 months less. Somewhere in there, it was that much less. I'm 90% sure. Okay, so let's go on to another problem. Let's get this one out of the way. Now, on the next problem, we are going to use, again, they give us all the data, but I'm just going to use the summary statistics again. When we go into the next section, I'll show you one where we input the data once we're a little more used to this so that we see what that's all about. Okay, so let's go ahead and jump from there. This next problem, it's 1046, but rather than telling you it's 1046, let's put it up here. And I'm going to put it over here on the right-hand side, because I'd rather write on the left than the right, and I'm not exactly sure why. Maybe I'll leave it on the left. And the reason is I don't want it to overflow the side of my page. So let's see. Let's go back to, let's go grab this picture. So I'm grabbing it from the file, and it's just the next problem, 1046, the next problem that was in the book. Okay, so let's put that there. Let's go ahead and kind of read this through. Gender and direction. In the paper, The Relation of Sex and Sense of Direction to Spatial Orientation in an Unfamiliar Environment, J. Scholl et al. Published the results of examining the sense of direction of 30 male and 30 female students. After being taken to an unfamiliar wooded park, the students were given some spatial orientation tests, including pointing to south, which tested their absolute frame of reference. The students pointed by moving a pointer attached to a 360-degree protractor. Following are the absolute pointing errors in degrees of the participants. So you may have heard something like this before where people talk about, oh, you know, maybe this gender. A lot of times you'll hear, oh, women don't have as good a sense of direction as men. And so that comes up periodically. Well, here's where they actually tested, hey, let's get some men, let's get some women, let's see who has a better sense of direction. So when I look at these numbers, it's how many degrees they are away from pointing south. So the researcher said, point south. And for instance, that first male was only off by 13 degrees. The next one across the top, he was off by 130 degrees. Now, if you're off by 180 degrees, you're pointing directly north, which is as far off as you can be. So you can see there's quite a difference in how well some people know their directions. So that 130, and as I look through, that was worse than any of the females. So notice the best, there was one male was only off by 3 degrees. There was one female that was only, there was 3 females that were only off by 3 degrees. So there's a lot more of the females that are better than a lot of the men. So let's see what happens here. Although we do see down here, X bar sub 1, 37.6 was the average error of the males, and 55.8 was the average error of the females. Again, we see there's a difference there. The question is that a big enough difference that we don't think it could just be sampling error? Okay, so it says at the 1% significance level, do the data provide sufficient evidence to conclude that on average, males have a better sense of direction, and in particular, better frame of reference than females? Now we have to be careful because we see this word better, and a lot of times we see better, we think, oh, something's greater. That's not what better means in this case. We don't need to say all that. In this case, when they say better, it means there's less error. So this, we're saying better, less error. So this one again is going to be a less than. So when we set up this problem, we're going to set up, I don't need any of that. Go away, go away. It's not going away. All right. So we're setting up our hypotheses. Our null hypothesis, mu sub 1 is equal to mu sub 2. So we're going to assume they have the equal errors. And then the alternatives is what the question asks. Oh, do the males, population 1, have less error on average than the females? Well, let's check it out. So we do know there's two populations. We do know that we have sample standard deviations. So they're t-tests. So it's a two-sample t-test. Now, remember, they did say that we can assume that everything's okay, that we can do a pooled t-test. Notice our sample standard deviations aren't that far apart. So it's possible that the population standard deviations were equal. And since both of our samples are about the same size, we're okay. If you have drastically different sample sizes and drastically different sample standard deviations, then you're not going to be able to assume at all that the population standard deviations are equal, and you would have to do a non-pooled test. Okay, so we're okay there. So let's just go in and do this again. I have the data, I have all my data here. I also have all my summary statistics. So when I flip over, we'll make this easy. All right, so we're doing a new test. So stat tests. And again, it's down at 0. I just hit 0, it pulls up 2 samp t interval. So we'll use this, and I'll read off these values as I put them in. So we've got our X bar sub 1, they told us was 37.6 was the average error for the males. The average standard deviation for the males, 38.5. There were 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. 5 times 6 is 30. So there were 30 males. That's not a 30. There were 30 males. X bar sub 2, 55.8. S sub 2, 48.3. And we're again going to say that there was 30 in our sample because there were. Oh, good heavens. I'm in the interval, not the test. Well, that wasn't very smart of me. Well, here's okay. I've already got that stuff put in there, so I'm going to be in good shape. Now I'm going to change this to a 98 because we're going to do a 98 next time we come by. But we're the t-test. Notice when I do this and I go through, it's not going to give me, and I calculate, it's not going to give me a p-value. I can't, it doesn't even give me a t-value. How in the world would I be able to figure out whether or not to reject the null hypothesis? Oh, it's because I'm in the wrong place. I went into t interval instead of t test. Make sure you don't do that. So let's go back. But if you get somewhere where you're saying, hey, that's not a p-value, it's an interval. Oh, I'm in the wrong place. We want to go to number 4, 2 samp t test. Now the good thing is all that stuff we put in is still in there. So now I just arrow down, do my calculation. Now I'm going to get my t value and my p value. So my t value, negative 1.61, and my p-value 0.0, let's go to 4 decimal places, 0.5. Well, if I go to 4 decimal places, they usually ask us to go to 3, don't they? I think they usually ask us to go, to 3 in the computer. So to 3, it'd be 0.056. If we went to 4, then that 9 would flip into a 10, and it'd still be 0.0560. So that doesn't change things a whole bunch. All right, so let's flip back over to our notes. All right, so we did a 2-sample t-test. We got a value of t equals negative 1.61. And our p-value, I said I didn't really have to write it up here, 0.056. So let's do this. I'm going to list my p-value, 0.056, and I'm checking to see if that's less than my significance level, which they told me this time, alpha, 0.01. That's my alpha, or my significance level. Remember, that's the risk I'm taking of making a type 1 error. I'm only willing to risk a 1% chance of making a type 1 error. And so when I look at these, oh, this is really, if I go 2 decimals, 5.6%. Didn't really like the way that percent came out. Which is less than or equal to 1, we'll just call it 1%. And we say, no, it's not less. I'm going to cross out the less thans and say, look, that's not less than, so I am not going to reject the null hypothesis. We usually say do not, don't we? Do not reject the null hypothesis. So what this is telling me, even though we had the big sample mean differences, one was 37.6, the other was 55.8. At the 1% significance level, that's not far enough to say that I think there was a difference. Now, do I think there was a difference? Well, it sure looks like it, but is that enough to be sure at the 1% significance level? Remember, I'm only willing to take a 1% chance I'm going to reject the null hypothesis if it's true. Reject it incorrectly, make a type 1 error. And this time, oh no, there's a 5.6%. Remember what the p-value is doing. It's telling us the probability, in this case, these two sample means would be this far apart or even further apart if the null hypothesis was true. And so they're saying, well, that we would get numbers at least that far apart 5.6% of the time. And I said, but wait, my cutoff's 1%. 5.6 is not rare enough. It's not less than 1%. So I'm going to say it's not rare enough that I can throw away the null hypothesis. So it may be true that mu1 is equal to mu2. The evidence isn't strong enough to reject that. So I don't reject it. And then to answer the question, remember that the answer is always in terms of the alternative hypothesis. So in this case, I say no. The data is not sufficient. And a lot of times what they'll say is not sufficient at the 1% level or at the 1% significance level to show that, how would they say it? Males have, well, we'll just word it that way, that males have a better sense of direction. And a lot of times the reason they will say at the 1% significance level is because notice, if I had a significance level alpha of 10% this time, I would have rejected the null hypothesis. So that's why a lot of times they'll put in the significance level. Oftentimes, when you read research, they just tell you what the p-value is. They don't say anything about, they don't make the conclusion for you. They let the author, or the reader rather, make the conclusion based on the numbers. So if I look at this and say, oh, 5.6%, that's pretty low, I'm going to reject the null hypothesis. Well, somebody else may look at it and say, oh, that's not low enough. I'm not going to reject the null hypothesis. So it just depends on how much risk you want to take of rejecting the null hypothesis when it's true. So what we're going to do from there, now we're going to do a confidence interval as well. So what I'm going to do, we're going to find a 98% confidence interval, and we'll go through that. We've already got the data, and I put it in confidence interval already. So find and interpret. I didn't say and interpret last time, but we did. A 98% confidence interval. And I'm just going to say for the difference in the means. I'm not going to word the whole thing because I'm writing it down. All right. So let's go ahead and do that. Again, we just jump to the calculator. So this will be quick because we've already got all the data in there. So we go stat, tests, and again, remember it's down at 10, which they list as 0. So if I hit 0, I get a 2-sample t interval. That's what I want this time. Everything's already in there for me. I just go down to where it says calculate. And I hit enter. It gives me the values, which I'll jot down on my piece of paper, negative 45.2 and 8.8. Notice I'm only going to one decimal place this time. The reason is, remember in our calculations, we usually go one decimal more than what our data was. Our data was all whole numbers. So when I do a calculation, I usually go to one decimal place. So let's do that. We'll flip back over. We'll state our interval. It was negative 45.2 to 8.8. Notice something in here. I go from a negative to a positive. That means 0 is in that interval. That means there might not have been a difference in the two. So again, this agrees with my hypothesis test. So remember, base this on the first population. We had mu sub 1, let's call it population. We had population 1 was equal to the males, and population 2 was equal to the females. So when I word this, I'm going to word it all in terms of males. So I could say this: we can be 98%. Did I do a 98% confidence interval? I don't remember. I'm going to go check real quick. I don't want that. Let me jump back. I apologize. Let's see what we did. It doesn't tell me there. If I arrow down, will it tell me? And 2, no, it does not. All right, let me check. You guys probably remember because you were paying attention. But I'm going to at least make sure that we do the right one. Confidence level 98. Okay. We are wording the thing. I would have just changed what we're looking at. We can be 98% confident. And again, just in terms of population 1, that the males that, we're not going to say the males, we'll just say that males, sense of direction, on average, ooh, I'm going to reword that. Sorry about that. Because remember, we were looking at sense of direction, but those numbers specifically refer to the amount of error. We can be 98% confident that, we rid of that too. The average error from the males was between 45.2 degrees less, that's a degree sign up there, that's not 20, and 8.8 degrees more than the females. So notice from this, I don't know who had more error. Did the males have more error or did the females? Well, it may have been as extreme as the males had 45.2 degrees less error on average, but it might have been all the way to the point that they may have had 8.8 degrees more error than the females. So since I don't really know convincingly who had less and who had more error, I can't say that there was a difference. That's why I wasn't able to reject the null hypothesis. So anyway, here's our conclusion. Bring that over from the other side. And that's the end of this section. We'll do another problem. I'm just going to do one problem from 10.3 because remember, the only big difference is if the sigmas, the population standard deviations, are not assumed equal, then we just don't pool the data. So here, and we'll just say that, since sigma's not assumed equal, do not pool the data. Everything else is the same. All right, so we're just going to jump right into a problem. So let me look in here. Now, if we were doing calculations by hand, there's some other stuff that we have to do, especially for the degrees of freedom. But we don't, in this case, have to do that. And I'll talk about degrees of freedom a little bit for the next. Now, from what we've been doing so far, if we can pool the data, the degrees of freedom is just, remember before when we had one population was n minus 1? Well, this time you add the n's, subtract 1 from both. So it's n1 plus n2 minus 2. So, and the reason I'm not writing that down is because we can usually just get it from the calculator. And I'll show you what I mean by that as we get there in this next problem. Okay, so here's what I want to do. I'm going to look at problem 1081. So we're going to pull that one up so you can see it. Let's see, 1081. See, that's what I mean about that being in the wrong place. Here, let's undo that. Let me put my cursor right here, and then I'll go do the same thing. So insert picture from file, 1081. Okay, so now we've got it in a better place. All right, so now let's go ahead and do this. It says acute postoperative days. Refer to example 10.6 on page 460. The researchers also obtained the following data on the number of acute postoperative days in the hospital using the dynamic and static systems. So I don't know if we've done this problem before, but they had talked about these. But this is the first time we've done it where we have both samples. At the 5% significance level, do the data provide sufficient evidence to conclude that the mean number of acute postoperative days in the hospital is smaller with the dynamic system than with the static system? Okay, so let's take a look at this. Again, we're going to do the confidence interval also, but let's start with the hypothesis test. All right, so let's do this. This time we're going to put in the data. So we'll start with the hypotheses though. We'll say mu sub 0, again, I said mu sub 0, h sub 0, our null hypothesis, mu sub 1 is equal to mu sub 2. Again, we always assume they're equal. Notice this is going to be population 1, this is going to be population 2. Just to make it easy, we just won't change the order of the way they're listed. Okay, so we go through this. Now notice this time we've got different sample sizes. And also our standard deviations are not very close together for the samples. Since those samples are so far apart and we have such big differences in sample sizes, this is when we're not going to assume the population standard deviations are equal. Now, again, they told us at the beginning, it says before these problems, preliminary data analyses indicate that you can reasonably use non-pooled T procedures. So since they don't tell us anywhere in here about assuming the population standard deviations are equal, since, yeah, because that's how you'll know in a problem that I give you, since they don't tell us sigmas are equal. Do not. Okay, so this one's going to be not pooled. Again, that's the only difference from the last section. Okay, so I've got this data. I'm going to go in and I'm going to put this population 1, I'm going to put that into list 1. Population 2, I'm going to put into list 2. So let's jump over and do that. All right, so let's go stat edit. And I've already got some stuff in list 1. I'll just arrow up, hit clear, arrow down, it's gone. So in list 1, I'm just going to put in the data they gave us. So they gave us 7, 5, 8, 8, 6, 7, 7, 9, 10, 7, 3 more 7s, 7, 7, 7, and then an 8. And there's 1, 2, 3, 4, 5, 6, 7, 14. Yeah, and that says 15 is the next entry, so I have 14 in there. I'll arrow over, it'll take me to the top of list 2, and I have 6, 18, 9, 7, 14, and 9. Okay, so I've got all my data in list 1 and list 2, so now I'm just going to go do my test. So again, it's a 2-sample t-test. We'll write that when we get back over there. But now we go stat tests, 2-sample t-test. It's number 4. So notice at the top, 2-sample t-test. This time I have the data, so make sure we select data. And my data is in list 1 and list 2. Frequencies are both 1. This one was a less than, so we keep it as less than. Pooled, this time we say no to pooled. And then we go down, we're going to calculate this one. And there's our calculation. Again, I'm going to write those down so we have them. The t-value, negative 1.65, the p-value, 0.078. All right, so let's flip over and notice they calculated X bar 1, X bar 2, standard deviation 1, standard deviation 2, and those actually match what they give us in the book. And I say that, yeah, and they do give us those in the book. So we could have skipped using the data and just used the statistics, but sometimes they don't tell us. We actually have to input the data. Okay, so we've got that. So let's flip back. Let's write down what we did. Okay, so mu1, mu2, I didn't write this down. The alternative, they said, are the mean number of acute postoperative days in the hospital smaller with dynamic? Well, that was population 1. So is mu1 less than mu2? And that's what I put when we did the hypothesis test. And what we got was we got a t-value. So that was a 2-samp t-test. We got a t-value of negative 1.65. And we got a p-value. I'll put this down here. Our p-value, let's put a line right here so that we know this is the test. A p-value of 0.078. And again, we check to see if that's less than or equal to whatever they gave us for alpha. They said 5%, 0.05. And again, no, that's not less. That's 7.8% is not less than or equal to 5%. So since it's not less, we do not reject. It's a weird look and see. We do not reject the null hypothesis. And then we answer the question. They said, do the data provide sufficient evidence to conclude the mean number of acute postoperative days in the hospital is smaller with the dynamic system than with the static system? We have to say no. The data is not sufficient to show, and then let's just abbreviate some things. Average days are less with dynamic than static? Yeah. Dynamic than with static. And that's our conclusion. Again, we will do a confidence interval for this as well. Now, I will tell you there's one thing that I think happens on the computer. So on my stat lab, when you're looking at p-values, if I don't have technology, so if I don't have a calculator, a computer, and I'm using the tables, this stuff like a lot of students have to do, I can't find the p-value exactly with the t-table. I can do it with the z-table, but not the t-table. And so what happens with the t-table, when I have a p-value for a t, a lot of times what they'll do is they'll give us a range. And they usually give us the range of, so for the p-value, they'll say, oh, it's greater than 10%. It's between 5 and 10%. So let's see. So we'd go 5% and 10%. The p-value is in there, so it'd have to be this way. Or it's between 1%. I guess I'll put a p up here. Between 1% and 5%. Or it's less than 1%. Now they can't have an equals with both of these 5%. I don't know where it would be. We'll take one of them off. We'll take off this one, that one. It does something along those lines, and you have to choose the right one. So they'll have a little circle on each of these that you need to pick the right bubble. And so on this one, we'd look and we'd say, oh, it's 7.8%. So it's between 5 and 10%. So we'd pick this bubble right here. We'd say, oh, it's this one. So you have to put it, and the reason is the columns in the t-table are numbered with these values. And so it has to be between some of those. So do realize sometimes they won't ask you to put in the actual p-value on a t-test because most students can't find it. We have to say, oh, it's between 5 and 10%. So that's how we would do that one. Okay, let's jump off, and we're going to do, since we had a 5%, let's do another 90% confidence interval. So find and interpret a 90% confidence interval. All right, again, we've got all the data in there, so this will be quick. So let's go back to the calculator. We're going to do a 90% confidence interval. So we go stats, tests. It's down at 0. Sample. We still have everything in list 1, list 2. We just need to change that confidence level. We're going to change that to a 90%. Again, it's not pooled because we can't assume the standard deviations of the populations are equal. And then when I go to calculate it, I get, let's see, these were days. So again, I'm just going to go to one decimal place, negative 6.9 and 0.6. And let's go back and interpret. So we did a 2-samp t interval. and we got negative 6.9 to 0.6. Again, zeros in there. That's why I couldn't reject the null hypothesis. All right, so here's what we do. Here's our wording. We can be 90% confident that let's not even say no, we still want the dynamic, good thing I looked, that the dynamic method had between, again, dynamic was population 1, had between 6.9 days less or fewer on average to 0.6 days more, because it's positive, on average than the static system. So is dynamic better? Maybe. But I didn't reject the null hypothesis. So I said, no, the data is not sufficient to show the average days or less, even though when I looked at my sample means, here, let's erase a couple of these things. So they're not in our way. When I looked at my sample means, the sample mean of the dynamic was 7.36 and the sample mean of the static was 10.5. So there's definitely a difference in the sample means, but is that enough to say the population means are different? Nope. Not at the 5% significance level anyway. Again, at the 10% significance level, we would have rejected the null hypothesis, but we weren't willing to take that much risk of making a type 1 error, of saying it's less than when it really isn't. All right, so anyway, that's actually the end of the material for these. I wanted to show you at least one of each type. We did 2 where we had pooled data, but again, I don't need to spend a lot of time in 10.3 because when it's non-pooled, we do everything the same, we just click a different button. So anyway, work on this, get yourself in a good position, keep up with the material so that when exam 4 comes, you're ready to get things done and do really well. All right, with that, I'm going to end the meeting and I will talk to you all later.